series. And so tonight we are joined by Peg. And so this is Karen M'Closkey, an associate professor, and Keith VanDerSys, a senior lecturer, both at the Weitzman School of Design at the University of Pennsylvania. And tonight they will be presenting us their lecture entitled Ground Control. And through a series of projects, Karen and Keith, who will join us for the Q&A section, will present opportunities enabled by recent advancements in digital mapping and modeling and how they shape our understanding of landscapes and environments. So with that, I will turn it over to Karen, who will go ahead and get started. Thank you all for being here.
Hey, everybody, can you see us okay? Hopefully, someone.
Yes, you're good.
Okay. Karen's going to present, but I'm just stepping in to say hi. Sorry we can't be there in person. Look forward to meeting all of you someday.
After, in the Q&A.
Okay, bye.
Okay, well, I'm going to share my screen and hopefully all goes well. Let me know if that's coming through.
You are good.
Okay, great. All right, well, as Keith said, I wish we were meeting you in person. It's just nice to meet people, see people, and I've never been to Knoxville, so one day. And I want to thank you also for the invitation. So I'm going to show a series of, really a selection of projects that we've done over the last 12 years, and also incorporate some of our written publications and some student work. So we're not going to go into too much detail on any one project, but we wanted to we're hoping that going for breadth rather than depth will give you a sense of the arc of our work over the last 10 years or so. So as Aubrey said in the introduction, a lot of what I'll be talking about today has to do with the changes to the tools of visualization that we use as designers and how that fits into a broader interest of ours, which is the topic of pattern. So the lecture is going to interweave visualization broadly with our projects and framed in part through the themes in our book, Dynamic Patterns, which was published a few years back. And so the topic of pattern is related to a conceptual shift described by philosopher Carrie Wolf, who argues that the framework of system and environment has replaced the categorical division between nature and culture. And patterns are relational, so they're conducive to this reformulation. And of course, recent technologies have made this world of patterns ever more accessible and given access to new ways of seeing our environment. Let's see if this advances okay, sorry. Can you see the next slide?
Yes.
Okay, I won't ask again. I'm gonna just assume all's going well. So humans have created tools to uncover the complexities that underlie our environment's immediately visible characteristics, whether microscopes or satellites or X-rays and so on. And so much of our knowledge about the physical world is produced at a distance through specific instruments and forms of representation. And of course, science and design are no different in this respect. And so the huge shifts we've seen in computation, which of course began many decades ago, but has exponentially increased since then, have an impact on our discipline and on knowledge formation. So one question we like to ask is, what do these tools allow us to do or see that we could not otherwise? And how do we use computation and simulation as tools to think with? So these are, just so you know about some of our writing, our school's, our department's journal, LA+, which is available online or in print. And Keith and I have guest edited 2 issues. Geo just came out a couple months ago, and then Simulation a few years back. And so if you have access to these, you'll see we're not interested just in the latest software or equipment because it's shiny and new, but because technology is not an isolated thing. It's social, it's cultural, it's political, and they all have histories. And as many scholars from fields such as science and technology studies and media studies have demonstrated, technologies don't simply precede or follow scientific knowledge, they arise in tandem. And so our environmental knowledge is produced through technical artifacts because there are assumptions embedded in the methods and tools by which data and information are collected and parsed. On the topic of simulation, again, this was a journal a few years back. Historically, within art and architecture and philosophy, of course, simulation's been understood as in a relation between the distinction between a model and its original and the copy, and the original is often nature. And so the two examples on the screen talk about simulation in two different ways. The one on the left is mimesis in terms of appearance, so it looks like the thing. We can understand there's vegetation and rocks and buildings. And then the one on the right, I can't see all of you, but I'm sure some people in the audience, maybe Jason Young, might recognize Pong. I think most of you are too young, but anyway, that's simulation in terms of behavior. And so the word simulation has had negative connotations in the past because it means to feign or pretend or give false appearance to. And if many of you probably know the allegory of Plato's cave. So as a philosophical concern, simulation goes back to the very nature of reality and questions about how we know what we know. So if we trace an arc from Plato's cave all the way through Baudrillard's simulacrum, then simulations are seen as a screen of signs that mask or displace reality. But of course, the other definition of simulation is less sinister. It's the imitation of the behavior of some situation by the means of a suitably analogous situation. So in that way, mimesis is an instrument for acquiring knowledge. So for instance, a simulation can be used to study a real world target at the level of processes and behaviors rather than just surface appearances. So what you're seeing on the screen is just a couple images from a seminar Keith did a few years back using computational fluid dynamics to understand wave and wind patterns to develop places for art installations in the Delaware River. So if we think about models, obviously models can represent in various ways and be made of different things, such as mathematical descriptions of physical laws. And then in design, we're very familiar with scale models, which are downsized copies of what they represent in the world. And so a simulation is simply an action performed on a model to understand behaviors. And physical scale models can be used for simulations if they're built for that reason. This on the left is Hargreaves Associates Guadalupe River Park project, and they and the Army Corps of Engineers built an 80-foot long mock-up of a river channel to test Hargreaves' design. So they used flows of colored water for eddy formation and sand for studying deposition patterns, and those became the vegetated and stabilized areas of the banks in the design. In contrast, the model on the right, the clay model of the same project, can't be used for simulation. Obviously, it doesn't have the right scaling properties, but this is just to say that the purpose of physical scale models and computer models is the same when running simulations, except that running simulations on computers, they can handle a much higher level of complexity and really provide a greater degree of flexibility in terms of testing various parameters and resulting scenarios. So simulations can provide real-time feedback. I hope you can kind of see this video. You might know the tangible modeling table that was developed at MIT in the early 2000s. NC State has one, we have one now at Penn, but it's a kind of tacit understanding of the relationship between like analysis and form. And so you can engage in that kind of feedback. And so really only recently has the development of fairly accurate fluid dynamic models and visual programming like Grasshopper, who I think I'm talking to architects and landscape architects, I hope. All of you are probably familiar with that. So it enables designers to work with this without in-depth knowledge of calculus or code. So it's been very incredibly influential in both fields. Oops. I guess maybe it's skipping. Okay, it's skipped. That's fine. So just in terms of a project that used simulation for predictive modeling, so not things that you can see in a physical model, but to predict, you might be familiar with this novel replenishment, beach replenishment program completed in the Netherlands in 2011. And they took like 21 million cubic meters of sand from the floor of the North Sea and like moved it to create this peninsula. And the engineers used this modeling to determine where to best place the sand to then let nature do its work of distributing the material down the shoreline. So the assumption being that it would lead to far less annual maintenance and trucks and emissions hauling sand than a typical replenishment would, because they only have to do this once every 20 years. But it offers the same protection in terms of storm surge. So computer simulations and certain instruments, let's see if this one's going to work. It's okay, it's just kind of a climate simulation, which I'm sure you've all seen many times. Computer simulations and other instruments, X-rays, radar, multispectral cameras, which I'm going to talk about later, reveal these invisible characteristics that lie beyond direct sensing. And so in these instances, we trust our simulations to tell us things that cannot otherwise be known, such as climate change. Obviously, the long-term trends of that are really imperceptible except through our computational tools. So these tools can help designers develop ways of learning that prioritize the relationship between form and process, and especially in landscape architecture, given so many of the places and issues we work on, these are highly variable conditions, and we think these tools offer a way to engage those variables. This is a little glitchy. Okay. So hopefully you can see our book cover, Dynamic Patterns, which was published in 2017. And it relates to the shift that I referenced in the beginning about the conceptual framework of system environment replacing the categorical division of nature and culture, and the role of patterns in this formulation. Because patterns exist outside of categorical distinctions, they don't really exist so much in things themselves, but only in relations between or among things. I'm just going to flick through a few of the images. The definition of patterns is that they are formal, material, or temporal recurrences, and they are essential for perception. We know that humans have an innate ability to recognize patterns, and we're really wired to seek them if they're not immediately visible. And patterns are also synonymous with processes, so they are indications of the forces and interactions that created them. And since many designed landscapes are constructed interpretations of nature or ideas about nature, but they're also physically embedded in living processes, patterns have an enduring relevance for landscape architecture, both representationally and materially. And of course, as our knowledge of nature changes, our depictions of nature change correspondingly. And as I've been saying thus far, the inverse is also true, which is that the tools and techniques used to measure and represent natural processes lead to changes in how knowledge is produced. So we drew inspiration from many sources, including Gregory Bateson and artist Georgi Kepish, who founded the Center for Advanced Visual Arts at MIT in the 1960s. And both Bateson and Kepish argued for the importance of pattern recognition as the central mode by which to engage environmental relations. And they were writing it and practicing at a time when systems thinking was really emerging as a powerful conceptual framework. Even though this framework is 75 years old, it has continued to evolve and has taken on renewed relevance. So we don't argue for the use of any one particular tool or medium over any other. In the book, we include many artists, some of whom work with data and algorithms, like Mark Nystrom, who makes these amazing plots out of wind data. But that's coupled with examples of other paintings or hand drawings, such as Bridget Riley or Emma McNally, who you see on the right. And then we look at the use of or search for patterns across many scales and realms. Many of you might be familiar with the 1998 Downsview Park competition, which included James Corner on the left and Bernard Shumay on the right. It was a competition won by OMA. But if you've ever read the brief of it, the framing of the competition was explicitly systems-based. And so in the book, we outline the centrality of pattern with respect to both systems thinking and ecology, and then their emergence in landscape architecture. And the various approaches to pattern finding and pattern forming that we see in landscape architecture today cannot be understood apart from the influence of system thinking. Well, in design more broadly, it's systems thinking, but through landscape architecture, it came through the field of ecology. And so we understand ecology and systems as common frameworks to describe the constellation of relationships that we see in the world. So we might call that the what of the world. And then patterns are the how, or the means by which we come to understand or know or express these relationships. So for example, we have a chapter on topological patterns, which looks at how processes influence form and organization, how those are geometrically and parametrically measured and modeled. Again, this is going to be familiar to both architects and landscape architects. So the underlying organizations and rules that we see in natural patterns, and how you can produce patterns by structuring relationships. And again, using Georgi Kebish's experiments with fire and sound, and Hans Jenny's work with sand and sound demonstrate the role of forces in shaping matter into dynamic but ordered formations using vibration, in this case, breath or a vibrating table in Hans Jenny's work. And then in terms of landscape, this can be helpful when trying to visualize things like air and water flow, which elude conventional surface descriptions, such as the use of contours to describe topography. So I'll show you an example now of one of our projects that use these two kinds of patterns. So flows expressed through gradients, and then also modularity as a surface expression. And this was the design build project for a stormwater infiltration trench in North Philly. I don't know if you can see my mouse or not, but you can see the site right here. And so to find a site, we looked at Philadelphia's Green 2015 plan, which was looking to convert vacant land into recreational space and green infrastructure, so stormwater collection. And that plan that you see on the right, it considered sites a 1/4 acre or larger, and then so that they could couple stormwater with things like schools and programming, recreation. And then so we decided to look at how many sites would fall under that metric, would fall under 1/4 acre. And it turns out of the 42,000 vacant lots in Philadelphia, 41,000 are actually less than a 1/4 acre, and that makes up 1/3 of all the vacant land in the city. So we then considered, we obviously couldn't look at 41,000 properties. We used other criteria, looking within, what you see on the left is a community development corporation. We looked within their sort of catchment, and then we added other criteria. Exposure, so who would see it, largest numbers of people might see it, so near bus stops and bike lanes. And then engagement was within 200 feet of a school or one of Philly Murals Arts, which is a really well-known program in the city. And then we also worked with the Water Department and Pennsylvania Horticulture Society. So this is just a sketch of the 2 water sources coming into the site, one from a parking lot, one from a roof. And then on the top, what you're seeing is a series of parametric flow models that define the rainfall quantities from those 2 points. And so any of you who've worked with Grasshopper know that these organizations are intrinsically relational. So you can take the volume of water and then just look at different trench configurations and profiles to contain it. So that's what the top drawing is. It's slope and water. And then the bottom left is a CNC milled plaster model of the surface from an earlier design version. And on the bottom right is a study model of how that surface topography could be expressed using a geocell. You may know geocells are everywhere in the landscape. They're just usually underground and we don't see them. So we basically just made a double wall configuration, which would give us the ability to control and alter the percentage of grass versus gravel. So that's some of the pattern studies we did. And the reason for doing that is just to have larger grass-filled cells at the endpoints of water to capture sediment, and then it can transition to more gravel and smaller cells. So it's about using pattern to frame function beyond standardized response. This is a very standard trench that you might see. They're usually just gravel or they're gravel covered in lawn. We're just really expressing that top layer of surface. And this is a technique we've used for larger sites. So again, going really fast through these projects, but competition for a 68-hectare park in Taichung, Taiwan in 2012, which was an old airport site. And the site for the park competition was the residual space, the green sliver you see. It was residual of the master plan that Stan Allen did. And this project was won by Catherine Mosbach and Philippe Rahm, and it's built. So if you're interested, look it up. They had an interesting premise. But basically, the Stan Allen master plan uses these 4 large circles to organize new development. And we played off of that, but kind of inverted it. For them, the circles were this kind of solids and fill, and we instead conceptualized these as spaces, as collections for zones where the most fluctuation would occur in terms of rain. So similar to the last project, we mapped the kind of roadway and inundation. Due to how the transportation was working across the site and the road infrastructure, it was already divided into kind of 5 sub-watersheds with sloping all to the south. So we basically map these. You can see the Hatcher drawings on the bottom, which show those different quantities, and use that to locate our circles, which you see on the bottom left. And those circles are really trying to index the volatility that's happening as with global warming and the volatility of weather. I hope you guys are okay because I see there's a tornado moving up. Anyway, so these visualizations determine the location and size of water collection. And so though they're geometrically similar in plan, the kind of ellipsoids that come off the circle, they alternate materially and topographically between forest and field and wetland, and then the circles really absorb and index this vacillation that we see between drought and deluge. So on the top right, the more controlled and maintained areas of the park are the kind of permanent wetlands and drainage, and then you can see in the bottom, the circular zones are the ones of more volatility. So they could hold rain and gradually release it during big storm events, or ultimately in kind of drought scenarios or lack of maintenance. How do you scale back maintenance where there's areas that need to be let go without losing the integrity of the design? So in this way, kind of borrowing Joe Nassauer's Messy Ecosystems Orderly Frame, so you can have more wild within the conventional form of landscape. So again, these are the two projects just to show you that the pattern pertains to geometric surface expression and also to the method of pattern finding through the kind of gradients. And so even though all design is iterative, you assess, you adjust, you reassess, I think parametrically enabled software really has the potential to relate the quantitative, in this case the rain, and the qualitative information through feedback. And it works in a three-dimensional form in a way that kind of GIS mapping and graphs or raster-based drawings cannot. So then another chapter is ornamental patterns in our book. And that's looking at geometry as an expression of nature using iconic or rule-based configurations that produce ornamental patterns. So how nature has been expressed in ornamental forms, whether based on rules or resemblances. So for example, vegetal motifs, they're interpreted in contemporary ways, as you see in the bottom left, as well as interpreting rule-based ornamental patterns on circles and hexagons. And again, parametric software facilitates rule-based explorations. We also include examples by contemporary practices like Westgate, who use botanic motifs in their work, and including work I did a while ago now with students in Las Vegas on the studio on ornament. So we've also used that in our own work, some temporary installations. I'll show you this one that responds to rainfall. So it creates an ephemeral pattern that's visible only when it's wet. And the pattern was created using a double circle. So it scales such that the overlap zones would create these differently sized floral figures. And so they can transform into like being isolated figures to a more field-like pattern. And this is just us testing it out. So we use laser cutters to cut the templates, and then we applied a water retardant, and then we kind of wet the surface. So you can see once it's dry in a couple of hours, it disappears. Another example of our use of ornament are our knot garden installations. And here we cut laser cut patterns out of weed control barrier, which is an expensive, again, another ubiquitous geotextile. In this case, this one's used to retard plant growth. And this is just to give you some of the context of Philadelphia's Clean and Green program that the Pennsylvania Horticulture Society does. What you see on the right, they clear sites, they regrade, they plant lawn, and they put up a fence to prevent dumping. And this is to have the kind of perception of a maintained landscape in these vacant lots. And so our goal was to derive, the same aesthetics of care, but maybe more visual options. And of course, to do so with minimal means, because there aren't a lot of funds to do things like this. So this is just showing the inspiration of the knot garden, KNOT, and then our site, which is next to a community garden run by the Urban Tree Connection. And then you can see we just made templates, laid them on the fabric, and just hand cut it. Then you roll up the fabric and bring it to the site. It's very easy, it's very fast. And in this case, we divided the site into two plots, test plots. And the first, we just kind of really simply cleared the vegetation put the fabric down, covered it in gravel. We wanted to see what would happen doing almost nothing. And then the other one, we dug up the vegetation, brought in a little more topsoil, and then seeded the circles and then filled the rest with gravel. So in the foreground, the one where we did minimal things, it started to grow in a little bit, but then as circles, but the creeping vegetation took over. But you can see in the back one, the second plot, it came in really well. And then this was a year later. Obviously, we did some maintenance in between, but the idea here being that there could be a patchwork of these because the vegetation on the perimeter is actually really useful habitat for insects and birds and critters. And then we did a second one, not again. And this is a kind of packing geometry. And we were able to use fewer templates because we just cut out 3 sets of 4, and then you can rotate them around each other as you move down the fabric. Same process where you cut it inside, roll it up, and then bring it out onto site. So these go in like 2 days at the most. It's really fast. And this one we used mulch, not gravel, because the cats liked the gravel. And it started to grow in nicely, but was run over by a mulch truck. So we didn't get to see it fully grown in. So then this brings me to the third thematic chapter in our book, behavioral patterns, and this is where a lot of our work has gone recently. And the context for this particular chapter is related very much to the 60s and 70s systems art. And again, talking, as I did in the beginning, about the system-environment coupling and the role that technology and data are playing in that formulation. And so, of course, as designers are increasingly asked to substantiate their work through metrics, we should remember that valuing only that which can be quantified or measured won't lead us out of our environmental predicaments. It requires a much bigger social and cultural shift that has to come through qualitative and aesthetic means rather than just a problem-solving mentality. Or at the very least, if we're trying to solve a problem, we need to remind ourselves of the persistence of interpretation that's embedded in any form of visualization, especially when it's data-driven, which can appear to be more objective than it is in some instances. So I'll explain. This is Wally, the trash compacting robot who roams the earth, and this is my favorite scene where he can't figure out where the spork goes. Doesn't go with the spoons, doesn't go with the forks, and he gives up. So, of course, this very funny scene reveals more profound and troubling insights than sorting utensils or laundry. We know that class, race, gender, sex, and so on can be deeply harmful categorizations, but they're not so easy to dispense with because classifications aren't just words. They're ideas around which all of these infrastructures are built. And they bind people to practices and narratives and routines. And so the more these classifications become embedded in our working methods, the more standardized and less visible they become. So for our field, mapping and cartographic practices embedded in our working methods is a perfect example of this. Abstract lines get drawn and then infrastructures are built up around them, making those lines very real and often very problematic. So the nature-culture divide and importation of particular ideas about conservation have not surprisingly been codified into maps and into laws that don't really account for change. So we've recently been working in the Galapagos Islands, that's my background. And it's a province of Ecuador, located off the South American continent. And most of you have probably heard of the Galapagos Islands. Its primary value to both scientists and tourists is its biodiversity, and also that it's considered very remote and very unaltered. All but 3% of the land is protected in a national park since 1959. And the Galapagos was also the first place to be labeled an ecotourism destination in 1969, which was thought to be a way to preserve it. The problem is that the fees paid to the island fund half of the national park operation. So more tourists is more conservation dollars, but more tourists is more waste, more goods, more introduced species coming in on food, the need for more energy and water and labor force. So to curb growth, immigration from the mainland has been outlawed, making Ecuadorians looking for higher wage work and the Galapagos illegal immigrants in their own country. And yet there's little controls on tourist numbers or operator licenses. So we might think of the Galapagos Islands as remote and pristine and locally unique. Certainly they are, unique and remote in some ways, but it's completely entangled with global economics and tourism and Western scientific views of nature and ideas of conservation that are based on a static conception of the environment, even though we know this is the seat of Charles Darwin's evolutionary theories. So the fact that someone in the 1950s drew a boundary around where humans could live and where everything else could live has everything to do with how this landscape is managed and funded. And again, this is typical of a Western conservation mindset, which I'm not suggesting is not important. I'm not suggesting conservation is not important, but it was conceived as a spatial problem. So it rooted all the problems in the 3% of developed land. And that created a divide and a lot of mistrust and violence even between conservation and some of the residents. That's improved over the last 2 decades, but still the amount of attention that's been paid to the national park has not been extended to the developed areas, and that's been our focus. The town of Baccaratza Moreno, which has about 9,000 residents on the second most populous island in the Galapagos. This is just to kind of give you a little flavor of it, because I want to show you a bit of student work. So I've made 2 trips there with students, both of which took place on San Cristobal Island with our guide here, who's a resident, Ernesto Vaca. And just to give you a little context of where the, this is San Cristobal. So these are the main islands, San Cristobal. And the town we're working is this little nub right here. And the hashed area is the rural area. Most of it has been abandoned farmland, which existed before the national park. So zooming into the town now, the gray are existing buildings and the orange is where it's trending. So we found that at current growth rates, the population could double in just 7 years, and that's going to fill its available space within 15 to 20 years. So everything outside of the park border. And if it keeps going this way without considering topography and water flow and vegetation, it's going to put further pressure downstream, which is where the existing town is. So it is amazing that one of the most famous conservation sites in the world, nature's prioritized, but landscape is not, which is nature and people. So designers can play a role just in terms of visualization of the islands, showing things that maybe might not be so obvious. And as I only have a superficial overview of some student projects, but want to introduce you again to some of these key borders that have been constructed in the management of the island. Even though they're well-intentioned and have had positive effects in terms of wildlife conservation, they've had consequences that undermine the very reasons that they were devised in the first place. So an urban park boundary, you cannot enter the national park without a paid guide. Residents can't afford paid guides. So many of them have never been beyond their own island, or they don't even know what the world is trying to save. And then the land-water boundary, which removed beaches and mangroves and sea lion habitat to create a kind of waterfront, conventional waterfront. And then the relationship of highlands to lowlands in terms of farming. This relationship is important, not just management and economics, but just topographically. So you can see, hopefully, the kind of blue hatch. Obviously, there's rivulets coming down everywhere. This is a volcanic landscape, but there are like 2 main ravines and 1 huge one that comes through the town. And they're getting channelized and they're building on top of them. So this is the ravines by the time they're almost at the beach. Obviously, the ravines are not lines, but they're being treated that way. And this, is, of course, is only going to get much worse as you remove vegetation and put more hard surface in upland. So using the individual student projects, we generated some principles that could show what a landscape strategy could be. Again, this is just drawing an axon to show the current situation. So the dark gray dots are existing buildings. And then, yeah, if you look, I'll go back again. If you look in this area, you can see where it's trending very quickly. So that's kind of business as usual. And so I've got this, if anyone's interested in this work, I'm happy to send you the studio booklets, which have more projects and much more of the context. But we pulled out some student projects that could actually kind of be put together. They all did individual, very select projects, but they could be put together into a larger framework. And And then we began work with images and models that use kind of webs and multiplicities of lines for analogs for thinking beyond the kind of single lines of the park border or the waterfront or the urban-rural divides. So for example, Dorothy considered a series of trails from highlands to lowlands that would give residents access, and also in terms of economics and tourism. So she thought about different trail networks that would diversify the experience for the tourist. And she developed 3 distinct trails, kind of transect terrain and stewardship. The train trail really emphasizes the experience of moving through this volcanic landscape. I mean, many people go to see the flora and fauna, especially the charismatic animals like blue-footed boobies, which I love, but it's a really amazing lava landscape. So how to show that more, which is what's giving life to these islands. And then the stewardship trail, which would involve locals and tourists under an umbrella organization such as the Galapagos Conservation Corps. And there's actually someone in Wharton now working on this piece of it to look at the feasibility of increasing the feet of the island just very slightly to actually start buying up some of this land. So it would have a different management strategy. It wouldn't be conservation of nothing can go here because it's been ruralized. So it could provide a kind of fourth, not just urban, rural nature, but a fourth. So another student looked at the kind of nature-urban boundary, which is strictly reinforced. As I said, residents don't have access to the park, so the kind of tortoise's neck, which is along the back side of the town. And his project was about transgressing that line with kind of small and strategic insertions that give residents access to these edges. So on the left is kind of the tourist experience, and on the right, those images is really like what you see in the town. And he connected the 3 high hills. One is the kind of a current visitor center and interpretation center. One is the provincial government home, which San Cristobal is. And then the other was a hill, but is now a mine. That's what they're taking down and using as aggregate to build the concrete for all of the town developments. It's a pretty interesting set of 3 hills. And then some strategically placed outcroppings and excavations that give views into the park or back out to the water. So this is just kind of a suggestion of what those views would be. And then, as I said, okay, so I'll quickly show you a third project. The seawall is built here, and the mangrove and beaches were removed in the late 70s, early 80s. So that took away storm surge protection and also removed important sea lion habitat. So a third student considered consolidating piers. When we were on our site visit, she observed that the various activities across the different piers rarely overlapped in time. So you could overlap them in space, so kind of consolidating them into a mega pier and actually providing more interaction among tourist residents and the fisher folk, who under early conservation, they were just, pushed away because they were considered harmful to the wildlife. But so here you have like just the kind of sunset pier, which ends up creating more beach. So it's kind of like a groin that collects them, the dock, and then the fisher folk with a market. And what this essentially does is by decommissioning 2 other piers, what you see on the bottom is you can build up more of that beach habitat because there's very little space for humans and sea lions are everywhere, and they're finding that the sea lions are becoming more tame to humans and more aggressive to each other. So that's just a quick bunch of student projects, but what I wanted to say now is that when I started the studio, I wanted to get the topography and bathymetry because I knew a lot of students would want to work on the waterfront, and we could not get them, we couldn't find the information that matched them, which is very common. So we contacted the INOCAR, which is the Ecuadorian Navy, and asked them, can you get us this information? And they said, no, we don't have it. Can you help us? And that led to some grant funding for Keith and some of our colleagues to go back to the Galapagos. To basically, the goal of the project was to make a digital model that joins the topography, which is usually one set of data, the bathymetry, underwater topography, which is another, and put them together. And then you can use that to simulate storm surge or sea level rise or tsunami modeling. So again, it's like one of the most scientifically important sites in the world, but no real basic data for doing any kind of modeling or mapping that has to do with the human residents. So the islands lack this topobathy model, and they also lack a unified datum that would allow you to compare elevations throughout the archipelago and make that analysis easier to do. So they kind of jerry-rigged some drones with better sensors and went down there to do the surveying. That was in 2019, so they collected visible light and also multispectral, which can better see the kind of shoreline and near bathymetry. And then made this model. This is 400 images stitched together to make the, I mean, it looks like an aerial photo, but it's actually a model, which every point is geo-referenced, so it can be used for running the simulations. And so I'd say that this kind of collapses the two versions of simulation I mentioned in the beginning. It's like it looks like the thing, it's mimetic in that way, but it also, you can use it to test behaviors. So computation certainly can mean more quantification, but it can also help visualize change over time. And so this is just a plug for the MLab, the Environmental Modeling Lab, that Keith and I and our colleague Sean Burkholder have started at Penn, and the kind of work that we're doing that you can see up in the top. So fluid dynamic modeling, the drone mapping, and just the kind of physical models like flume models. So modeling environmental systems can allow design iteration to be coupled with potential physical and numerical outcomes. So again, testing ideas, and then maybe provide additional criteria for decision making because you're able to run those various scenarios. So we've been fortunate over the last 2 years to be able to work at the Wetlands Institute in New Jersey, Stone Harbor, New Jersey. And this is, Sean has a lot of work with the Army Corps in terms of living lab and nature-based solutions. So this is all kind of happening together. But again, it's doing kind of experimental field research for collecting data. In this case, this is a coastal wetland. And these pictures are from a class that Keith and Sean teach on remote sensing and multispectral analysis. And a lot of the work involves comparing the kind of satellite data with the data you can collect in field. So like the Galapagos Islands work. And this red square that you see is the next slide. I'll be zooming in on that area. That's where we're surveying. There's not really time to go into the nitty-gritty of what multispectral imagery is or how it's achieved. Maybe in the Q&A we can talk about that, but it's really important to change and how change is understood, the magnitude and character of change. This land cover, what you see on the left, land cover information is basically what scientists are using over the last, it's been many years, but with satellite sensing the last 40 years. They use national land cover data sets to catalog and classify the Earth's surface. Most of that's been derived exclusively through multispectral satellite imagery. So when you download info on a GIS file to make a map that has anything to do with land cover, which is like forests or agriculture or wetland, all of that, most likely that's come from multispectral imagery from satellites. So the problem with land cover classification, thinking back to Wall-E, where does the sport go, is that every pixel can only be assigned one category. So that's, and that category is determined by the predominant material. So a pixel can mean like 30 meters by 30 meters, which obviously can have more than one thing in it, but when you have to classify it, you have to pick. So that's how the Earth's surface gets divided into homogeneous and simplified groupings like forest or open water or wetland. And so we're just looking at this and experimenting with it and trying to understand it better. What on the left is what's available from existing data sets like Landsat. So if you were to download it from state or national. And then on the right is the classification process using the data that we collected on site. And the difference between the two is we could differentiate 3 key salt marsh zones, so mud flat, low marsh, and high marsh, and compared to the left, which is just one, it's either open water or marsh. So classification can be problematic, but in the site-based surveying, it does give you more heterogeneity in terms of your land cover. I mentioned the problem with drawing clear lines of distinction rather than looking for relationships and patterns among things. However, land cover is used for pattern study. That's basically the field of landscape ecology, is the study of patterns at a landscape scale. And land cover is instrumental to that. Land cover maps are used to study and to measure and monitor change over time. So how much forest loss is there? How much has a town grown? They're also used, land cover is also used as inputs into simulation models, because the material matters to water behavior. So it matters whether it's concrete or mangrove or high marsh. So even though it seems kind of contradictory, fixing land cover in place is the primary means by which so much of this change is gauged. This is just an example where we ran 2 models for comparison. So on the top is the standard land cover map that you get from the National Land Cover database. That's what you see there. And then on the bottom is our model. So if you look at this kind of over time with the sea level rise storm surge model or a SLAM model, you'll see that the National Land Cover actually shows more total wetland loss, but the losses that our model shows are considered the more important losses in terms of you're losing edges, you're losing high marsh, and they're very important for nesting grounds for migratory birds. So the Wetlands Institute, who we're working with, we're doing this work with them, they're very concerned about the kind of high marsh loss. So this method can be used to monitor change to the area. So they're going to be putting in kind of new sediment, and then we will be resurveying it to see how that changes over time. But of course, our interest in experimenting is not just about accuracy or novelty. As hopefully you've gathered from what I've been saying by now, image interpretation is not mechanical, it's not impartial, and the plurality of interpretations mirrors the inherent variabilities and complexities of any landscape. So, but we feel that as frequent consumers of environmental data, we'd like to have a greater familiarity with all the embedded biases in the data sets we're using rather than just taking them for granted. So on the screen, this might appear to be a tidal fluctuation over time. It could be the difference between high tide and low tide. Hopefully you can see it's big enough that you can see these areas are shifting size. But it's not that. It's actually the exact same image. It's just interpreted through different spectral wavelength and algorithms that are used in remote sensing. So it's the exact same image, just interpreted differently, and that would lead to different conclusions if you were looking at how much high ground exists or where rising seas might have the greatest impact. And so this is the same thing, just shown all on top of each other. So each line depicts where the land water boundary is seen by these different indices that you apply to the image. And they vary as much as 300 feet, like in terms of horizontal distance. So that's just a way of saying that you get very different answers for where the shoreline is depending on the algorithm. And in most cases, you would never know. The data that's available to you doesn't actually list that kind of in its metadata, so you wouldn't know. So in this way, the creation of our own models and maps helps us know what we're kind of looking at, but it doesn't do away with the concern over classification, because comparing the same location across time or running simulations using similar baseline conditions still requires that you set a datum. And that can be a really fraught exercise, especially in coastal environments when everything is in motion. This drawing's a work in progress right now. We're trying to figure out the best way to show how the periodicity of the tidal cycles and of the satellite orbits and of the plant phenology, which is how you're reading wetland change, they don't sync. So even though you can get a Landsat returns to the same spot every 16 days, so you can get an image of the same spot every 16 days, that water elevation, which is the same way as saying the land location, are going to be different in those images. And along the Atlantic coast, the same water elevation can only be detected twice per year, given Landsat's orbital path. What this drawing shows is every time there's a cloudy day, you also can't get information. So the faded back are the cloudy days. So over a 3-year period of Landsat image, you can see there's a cluster of images that are useful. And then how many times do those images actually line up with tidal water? These are all things you have to know if you're going to do any of that storm modeling or monitoring over time. So we think that like working with these tools actually compels us to understand the implications of different ways of classifying data really to grapple with representing the cycles and asynchronicities that constitute our landscapes and environments. In fact, they actually showed the difficulty of distinguishing between landscape and environment, even though so much image interpretation is devoted to their separation. So rather than using static boundaries, representations of surface conditions as gleaned from remotely sensed images and maps could reflect the uncertainty embedded in their processing and delineation. So we're working to kind of develop ways that we might do that. So just to close, yeah, right on time. So one of our favorite quotes by Lawrence Halprin, variability, uncertainty, flux, they're central to our design vocabulary. And we need modes of visualization that can help foster this approach as well as convey it to others. And that's why we find simulation and pattern finding so relevant. Even though our focus has changed over the years, as you've seen, it's still about the pattern recognition for framing or drawing attention to or understanding cycles and growth and change. And in terms of exploring the recently available tools such as the surveying that we're doing, we think it's important to understand how these tools are used by others, whether those others are scientists or corporations, because the vision of the world created with them has consequences for knowledge formation, and therefore how we act on that knowledge and how we design with that knowledge. So I'm going to stop share. Did that work?
Yes, thank you so much, Karen. That was an amazing presentation. Very, very relevant for a lot of our landscape students, as well as the architecture ones and interior and graphic design that are tuning in. Yeah, so we have so all across the board. And to our audience members, if you have questions, feel free to submit them through the Q&A feature at the bottom of the Zoom screen. And I just wanted to open up with a question that is it's not exactly about your work, but it's about kind of how you got to where you are today, and kind of your trajectory, I guess, from being a student to this space now.
So yeah, Keith will come join. Join me on the beach in the Galapagos.
Join me on the beach, exactly.
Wow, how did we get here?
It's all her fault.
So actually it started, we've been at Penn for 12 years. I'm trained as both an architect and a landscape architect, and spent 5 years at University of Michigan with our Jason Young, who was our colleague there. And we got into academia quite early because it gave us the opportunity to do non-standard projects. I mean, we did have client-based practice for a while. The image you had on the screen to introduce us, that was a project that I didn't show that we did out in San Francisco with Bionic. So we still do that, but a lot of the work is kind of grant-funded, self-initiated, research-based, and we just love that we can test ideas with students and also write about the ideas, learn the different tools. So it's just, I guess it's been, we didn't have a plan 15 years ago to say that we'd end up exactly where we are, but we've kind of followed our interests and opportunities, and we're lucky enough to be in a position where we can do that. I don't know if that answered your question, but.
Yeah, definitely. That's awesome to hear of your trajectory as well. And I know some people on this call, including myself, are transitioning from architecture to landscape architecture. And so that's a very relevant kind of trajectory for us to be thinking about as well. And I also wanted to ask another question about like the material choices that you had in some of the experiments with patterns, and how you kind of decided to use those, I guess, more ordinary materials rather than going with something that was a little bit more avant-garde, I guess.
Do you want to answer?
No, you start,
Okay.
and then.
So that was an example. So the kind of geocell and the knot gardens, that was an example where we actually were doing some client-based work out in California, and kind of using those materials. I mean, the weed control barrier is everywhere. and it was kind of one of those things where we were simultaneously had been working on the topic of ornament with my studio at a totally different scale. And it just sort of, the two kind of came together, like why, if this material is weed control barrier, then it doesn't need to block everything. It was really kind of a simple idea, but something very inexpensive, very easy to do. And with the tools we had, I mean, coming out of architecture, we came to Penn in 2007, 2008. So obviously ornament and architecture like had really preceded than it did in landscape architecture. And so we had been working with digital fabrication like in Michigan. And so we came with the kind of architecture mindset of using those tools experimentally, and that we found a landscape application.
And I had concurrently been teaching a digital fabrication seminar in landscape architecture. And part of the impetus for that was looking at very ordinary materials that pervade and really structure kind of unseen the surface manifestations of all of the living material, and how you might use mass customization and digital fabrication to take those unseen materials and give them new surface performance and new surface aesthetic and expression. And that especially became, I think, salient as we started to think more and more about that relationship between the ephemera of the environment and how it could be responsive to the vacillations of the kind of changing context or milieu. And it's usually not thought of that way. It's usually applied in really uniform, generic, and efficient manner, but just giving it a little kind of addition of a parameter in that it is also expressing an aesthetic dimension of its environment, really, I think, was opportune for those particular materials.
Thank you, that's great. Okay, and so moving into a question we have from Professor Mark Stanley. He says, thanks, Karen, for the great talk. I'm wondering about the balance between perfection and imperfection. You seem to serve such a balance, using extreme precision to work through imprecise mediums and vice versa.
That's a great way to put it. Thanks, Mark. This is a really great question. I guess I might use the word precision instead of perfection. This question of precision has come up a lot in the survey work. So precision, when we think of precision in terms of the early projects, and that has so much to do with craft of the material, and we care very much about that, the material and the detailing. When it comes to craft of remote sensing, it's not, it's in how you're trying to understand and use the tools. And Keith is the expert on this, not me, in terms of trying to get the models to match reality as much as possible. And there, the question of, I think landscape architects are generally very good at working with precision in terms of detailing and material. When you start talking about precision versus accuracy, that's kind of a different thing. And the later work kind of we have to know how it's accurate or not to know how useful a model is. And that's a kind of a more complicated question, because so much of it in the interpretation and how you're using the tools, there is a kind of range. But I really like that question about the imprecision of the medium. You're working with living medium, and sometimes you can precisely control it, the medium, like the growing medium, through simple maintenance. But in the later work, it's just it's a kind of different animal.
I mean, just the only thing I would add to that is the ability, and I think we reference it a lot in our book, to understand change is to have fixity. And so to have something in which to register change against, so you can allow for a certain level of unruly and emergent behaviors as long as they're registered against something that has a degree of regularity. and hence the kind of precision in the regulating datum against which change is happening.
That's a very good question. Thank you, Mark.
Yeah, thanks, Mark.
And so we also have a question from Jason Young, who you all know very well. He says, thank you for sharing your amazing work and sharing it with us. What is a post-Euclidean groove and how can I get one?
This is an insider joke because no one else other than maybe Jason and a few other Michigan folks know that PEG stands for Post-Euclidean Groove. Good memory, Jason.
Mm-hmm.
We don't say that anymore, but it was kind of a joke. Post-Euclidean groove was a phrase that Aldo van Eyck used from Team 10, and he was critical of the architects. He did the quote in his 50s or 60s. I'm forgetting the exact date now. And he basically said,
modernist planning.
Yeah, and the rigidity of it. And he said architects need to get beyond the Euclidean groove. And like when we were reading that, we like, oh, we like that phrase, so we just named ourselves PEG.
Yeah.
So I don't know where you can get one, Jason. There's only one.
Fantastic. I'll have to look that up for sure. And so we have another question. This is from Professor and Director Yale Fulton. Can you talk a bit about how your use of models and simulations have allowed you to collaborate differently with other disciplines?
Yeah, that's also a spectacular question, and that's something we're still wrestling with. Is how do we bring into our discipline, the discipline of design, tools that are prevalent in our allied fields. So when we're working with structural engineers, civil engineers, when we're working with biologists, when we're working with acousticians, whatever the case, they have particular models that they use to optimize certain functions and performances. And they're very potent and important to starting to tune and calibrate either the armature, be it landscape or architecture, to that particular function or performance. So then you start to ask questions that what if they can take on additional work? What if they can take on additional kind of questions and functions that aren't optimized to single behaviors and take on more synthetic and let's say multifunctional or kind of multivalent parameters and outcomes? And so then you start to utilize their tools as a basis to share a vocabulary, and one that's particularly driven by time, kind of interaction, and interdependency with a bigger set of, let's say, influences. And so suddenly you start to find ways of questioning, probing, and exploring that through the same language, but outside of the kind of singularity in which those models and the simulation is typically used for. So kind of I don't have a good answer for that yet. It's one that I think I'm still working on. We're still working on that one. But being conversant and facile in that language is an obvious benefit to the interdisciplinarity of our disciplines.
I mean, so in the Galapagos, that was information we wanted. So we weren't collaborating with another discipline, although they are engineers at the Ecuadorian Navy. They needed our help in that instance. And that's also what's happening at the Wetlands Institute. They don't have the means to do this themselves. So in that sense, we're testing out our ability to actually help them with their goals. So that's a very, again, a particular example. And
so wrapping into this next question, I have a question about how do you overcome feeling limited by the data that's available? And this kind of ties in with the next question, which is, are there other surveying tools or mediums besides satellite imagery that you use or want to use to overcome these limitations of Landsat that you've described at the end of your talk?
Yeah, that's also a really salient and potent question. One of the things, and maybe a little bit more so in landscape architecture, but I think it's becoming more prevalent in architecture as well, just environmental performance and environmental behavior. We're becoming more and more vast consumers of environmental data. But then we're also hamstrung by the bias and the agenda for collecting that data. So there has been an explosion in the, say, last 5 years of commercially available, I think fairly economical, remote sensing, surveying, and kind of collection tools that we all have at our disposal. And there's in some way, an expansion of like citizen sensing, citizen science, citizen remote sensing that is enabling us to become not only consumers, but makers of data. And how we can start to do that really frames our understanding of what we could say is the context or the nature of the condition in which we're working, and make data that's suitable to the questions that we're probing. And so that's been one of the, I think, huge benefits of it's just, I would say, kind of commercially available remote sensing surveying tools that are fairly open source and fairly easy to understand how to manipulate them.
That's great. That's what we like to think about, especially in like the landscape studios as well, just thinking about how to manipulate this data so that it kind of works to not frame what we're interested in, but like frame kind of the topic we're looking at. So that's something that we've talked about as well, like avoiding solutionism. And so I guess that's something else you guys could, if you could touch on, like how you work to avoid that in your practice in the studios you teach.
That's been one of the kind of transformative dimensions of a simple, once upon a time free and open source piece of software like Grasshopper. The ability for landscape architects to become tool makers, or architects become tool makers and not just tool users, is absolutely transformative. The ability for us to start to have tools that respond and extend our design methodologies that aren't driven by the commercial market, I think is utterly transformative to design vocabulary and methodology.
Great, thank you. And so I have one last question, and this is mostly just talking about like the current state that we're in with the pandemic, and how has your workflow changed or not with having to work from a distance rather than working on a site, for example, not being able to visit the Galapagos right now?
In the case of the Galapagos, that work, like that we need to do the mapping of the other islands. We just can't do it. And we're not going to go until Ecuadorians are vaccinated, and that could be quite a while. So that really is on hold a little bit. And in terms of studio is going to be interesting. We moved one of our core studios to the summer, and we're going to have students who aren't in Philadelphia, can't get here yet, and they're going to be doing a site remotely. And I'm sure many of you have done the same thing if you don't have access. I think it's an interesting challenge and learning experience, like how much, I do believe site visits play a very important role in how you conceive of a project, how you understand it. When you don't have access to that, what are all the proxies that you're going to use to try to get that? So it is a challenge in terms of the New Jersey work, that's easy.
Yeah.
We can just get a car. It's an hour and a half away, and we were there last week, and Keith will be going next week. So that's
We're-
not a problem.
We're outside on a boat.
Yeah.
On a tidal wetland, so it's not it's not as problematic. I'd say the only upside, there haven't been a lot of upsides, obviously, but the only upside in the context of academia pedagogy is I teach primarily now media courses, and it has given me the opportunity that maybe there's different ways that we can deliver content for our courses that don't always rely on in-person learning. And I wouldn't have had that, I think, whoa, I just disappeared. I wouldn't have had that insight had I not been forced to deliver an entire course virtually. So I think there are opportunities that can be gleaned from it, like make lemonade out of those lemons.
Yes, definitely. I think we're all trying to do that. And thank you all so much tonight for being with us over Zoom. Of course, not the ideal format, but thank you so much for sharing your work. And we look forward to hearing from you all in the future.
Yeah, thanks for the invitation, everybody. Yeah. Thanks for coming. And if you have any questions about any of the projects, just don't hesitate to reach out to us. We're happy to answer questions or send you more information.
And thank you, Aubrey and Carrie, for doing an amazing job with setup and moderating. Yeah. Really spectacular.
And Julie for the invitation.
Yeah, thank you, Julie. Sorry we don't get to see you and Keith in person. Hi.
All right. Thanks all.
Thank you.
Have a good night and weekend.
Yep.